talk a little bit about the gas used in the GC. As the name calls, gas chromatography is using the gas as a mobile phase. And the function of the gas is to take the sample throughout the column from injection port onto our detector. It must be inert, so it doesn't interact with our samples, with any components of our sample. And it is important to have the carrier gas of the high purity, as contaminants can chemically attack the stationary phase in our column and destroy it. And the common gases used in the GC are hydrogen. At the moment, this is the best gas to use on the market. However, it is explosive. Helium, it used to be the most popular, the most used gas in the GC, but due to non-renewable nature and increasing costs, we are looking to replace this gas with alternatives, and such as helium and nitrogen. But the helium is the most inert from all of the gases used in the GC. That's why it was very popular and very suitable for this type of analysis. And the third one is nitrogen, is somewhat viscous. So comparing to the other two, our analysis will take a little bit longer time. So I've mentioned those three gases, the helium, hydrogen, and nitrogen. They are used as a carrier gases, so as our mobile phase. But we can have also in the GC different gases to be used as detector gases or makeup gases. And here I've got an example of hydrogen, which can be used in FID as a fuel gas in our detector, and some other detectors as ECD or triple quad MSs. They can require the presence of the makeup gas or collision gas, and this we will call the makeup gas. And different gases can be used in this area as well. Going back to our mobile phase, so mobile phase gases, nitrogen, helium, and hydrogen. Here we've got example of the analysis which have been done the same way, but with use of three different gases. And each chromatogram in here has 20 minutes time span. And you can see the comparison of the analysis time, of the retention times when the different gases are used. So we can see clearly that when nitrogen is used, the peaks are eluting much later. So the analysis is taking the longest time when we compare this to helium or nitrogen. Helium, it's falling in the middle in the range of the retention time and analysis time. And hydrogen, you can clearly see that the analysis time is the shortest, especially when compared to nitrogen results. We do have also here marked the resolutions of the pair of the peaks, which we've chosen here. And as you can see, the resolutions also differ between gases. So different gas will have an different impact on our analysis, on our resolution, as well as on the analysis time. So why it is important to have the clean gas of the high purity in the GC It is critical to our instrument performance and also to our results. All of the gases can contain some contaminants such as moisture, hydrocarbons, oxygen, halogenated compounds, carbon monoxide, sulfur molecules, ammonia, siloxanes. So all of those contaminants can interfere either with our analysis and can show up on our detector, or can as well interact with our consumables, affecting our results, so accuracy of our results. So the gas should be purified before entering the GC system to avoid any interactions of the contaminants with the instrument and our consumables. So talking about the gas filter, I will explain you here a little bit what different options we do have and which one could be better or worse for your work, for your application. So I would like to differentiate here the first that we do have like inline gas filters, and we can have also the cartridge systems. And the differences are the inline filters usually have much higher capacities. They can be available as indicating and non-indicating. The cartridge systems are always indicating, indicating where the filter is depleted. The difference between the cartridge system and inline filter is usually that the cartridge system the cartridge is can be replaced on its own. We will have the fittings present to replace just the cartridge and not the whole body of the filter. And the replacement of the cartridge can be done easily without any tools. So then the fittings here are commonly used for inline filters are the compression fittings, or quick connect fittings are also a good option. The compression fittings are the most popular, the most cost-effective option. However, if we would like to minimize the downtime and make the replacement of the filter easier, the good option to choose will be the quick connect fittings, where we installed one part of the fitting onto our gas line, and then we would have to just replace the body of the filter without the turning of the gas. We will be able to replace the filter much quicker comparing to the standard compression fittings. Then we can have fittings with different materials. I'm mentioning this here due to different suitability of different materials for different gas lines, as well as for your awareness that globally we are facing increased number of regulations which are limiting the lead content in the brass, so the brass fittings will be less and less available on the market, and we will be making shift toward the stainless steel fittings completely. But the brass fittings are ideal to be used with copper tubing, which was used in our laboratories in the past. Nowadays, the stainless steel tubing is the most common option. So if we do have the stainless steel tubing, if we do have our gas lines made of the stainless steel tubing, we should be using the stainless steel fittings, not brass. And that's because the brass can is softer than steel, and we may observe galvanic corrosion when we do have the brass fittings of the filter installed on the stainless steel gas line. So fitting the filter, so it is very important to mention here how we should mount the gas filters in our laboratory, so either on our wall or on our benches. The filters should always be in vertical position, not horizontal. In a vertical position, the gas is able to penetrate the whole bed of the adsorbent, so all of the gas can be filtered without any void volumes. When we do have the filter installed in horizontal position, sometimes the void volume can be created at the top of the absorbent bed, and this way our gas is bypassing the adsorbent bed, so that means it's not filtered. So for the best results, for the best use of the gas filters, we will always recommend installing them in vertical position. So different classification of the gas filters. They can be also divided for indicating and non-indicating. Non-indicating gas filters, they are usually made from stainless steel bodies. The ones with visual indication of depletion can be made from various materials, but they will have a visual indication of the filter depletion, so we will know when our filter is not longer good for use, when it needs replacing. So here we do have photos of our indicators, so the materials which will indicate the depletion of the gas filter. So going from the left, we've got moisture indicator, and at the top, the green color is where our filter is good to use, it's new. At the bottom, how it looks like when the filter needs changing, so when the filter is in depleted state. In the middle, we've got high sensitivity moisture indicator, and on the right, we do have oxygen indicator. So at the top, again, when the filter is good to use, at the bottom, when it needs replacing. So we can clearly see different colors, and on our indicator we will observe the gradual change of the color, so we will know when our filters needs changing. So a little bit shortly about how our filters works. So here we've got diagram of the gas flowing through the filter, through the media. We've got nitrogen gas with various contaminants such as oxygen, carbon dioxide, carbon monoxide, some particulates. The gas with contaminants is flowing through the media and it's being filtered out. So that means all the contaminants are being trapped in the purifier media, and then on the outlet we've got only pure gas. So we are getting a very high quality of the gas. So we do not have any contaminations in our gas line after it's been filtered. And it is beneficial to use the gas filters for the gases of a lower quality, as the gas purification, the gas purifiers may improve the quality of the gas, so it may improve our results as well. And here we've got a graph chromatogram showing us the differences between the signals in MS, where the gas was used without gas purifier and with gas purifier. So plot A is where we do have a very high purity chromatographic grade helium. As you can see, the purity is here 99.9999%. And plot B is a lower quality of the gas, high purity grade helium, with purity of 99.995%, so lower quality than in plot A. But in plot B, we've installed a gas purifier. So as you can see here, the plot A is higher, the plot B is lower, and we would like to have a lower signal from our gas on our detector. So plot B is looking much, much better in this case, where we've installed a gas purifier to the lower quality of the gas. So the difference is here that the decrease of the baseline noise, and it will also increase our detector sensitivity if we do have the gas filters installed. It is also worth noting that each contaminant can be filtered out on its own. So we can have 3 traps filtering either oxygen, moisture, or hydrocarbons, or we can use one purifier which will remove all of our contaminants in as a one device in one go. And here we've got 2 chromatograms again, showing us the high bleed and low bleed. So contaminants in our gas lines can lead to column deterioration, and I hope that you remember from our last session how we can avoid the column deterioration, or how we can stop it, and what signs are telling us that our column is deteriorating. So one of the factors which will lead to column deterioration is the presence of the contaminants in our gas line, and this will be leading to the high bleed of the column, so the noisy baseline as well. And septa will be degrading much faster when we do have the present contaminants in our gas line. And as you can see on those chromatograms, the high bleed is causing the difficult quantification, not very nice chromatogram to analyze. With low bleed is the chromatogram which we would like to see, nice and easy to analyze. And also the moisture and oxygen can shorten the lifetime of our column, or can even lead to complete deterioration, so the change of the column for new one. So what is good in using the gas filters? What benefits we would get if we do have them installed in our system? So presence of the gas filter will lead to less detector maintenance. So our detector will be not getting as dirty as quicker. Our column will last longer, so we can save up a little bit of our budget on not replacing the column as often. It will lead also to better sensitivity of our detector, especially at the higher temperatures. Our chromatogram will be looking good and nice and better for analysis for longer, so our integration will be nice. And also this the presence of the gas filter is enabling us to use lower quality, so the cheaper gas without impact on our data quality. And here I've listed some questions which would help us to choose the gas filter. I know that the choice of the gas filters is massive nowadays on the market, and it can be very often overwhelming for us to choose the right one, but the starting point would be those questions. So how we would like to use this filter, what contaminants we would like to remove. It's also important to know our flow rates and the pressures, as different filters may have different requirements for that. How long our filter will be used, if it's 8 hours a day or it's the continuous use. If we would prefer to have the depletion indicator, as I've mentioned earlier, if we would like to have either inline system or cartridge system. I know this is a lot of factors to consider for choosing the gas filter. However, please remember that we are always here to help you, to support you with providing you the best option for your application, for your laboratory, either if it's for GC or any other applications. So now I would like to move away a little bit from the gas filter, but as we are talking about the gases, it's worth noting that our system shall be somehow sealed. So our connections are good, so the gas will not escape, so we will not have the gas leaks anywhere. And for that, we would require ferrules. Also, we may want to connect either guard columns or different columns together, or split our signal within the GC. So we would need different types of connectors as unions and splitters. So I will start with the GC ferrule. So the function of the ferrule is to maintain the sealed flow path of the gas within our system. The ferrules are used on both ends of the capillary columns, so at injector end as well as detector end. And the main considerations for choosing the ferrules is the ferrule shall provide the leak-free seal with the minimum force required for that sealing. It shouldn't stick to the column or fittings and should be suitable for our temperature of our methods, our analysis. And here we've got diagram, a little reminder of the injection port, how it looks like. And we've got marked here at the bottom that the ferrule sits on our column and it's fitted there using the column nut. And within the ferrule range, we can have different materials. Different materials are available. And here we do have the most common ones, like the Vespel, different mixtures of Vespel with graphite, PTFE, and metal ferrules. They've got different hardness. So as you can see, the polyamide, so Vespel and Vespel graphite ferrules are hard, as well as the metal ferrule. PTFE and graphite is soft. All of the ferrules here are suitable for GC, but one of them, so graphite, is not suitable for GCMS due to its porosity to oxygen. So please remember, if you're using the GCMS, don't use the graphite ferrules. Any other will be good, but the graphite will be good for any other detector, but not for the mass spec. Different materials will have also different temperature rating, so the choice of the material will be dependent on our analysis on the temperatures which we are using. And due to the different nature of the materials, some of the ferrules require retightening after first few cycles of temperature, and can be either reusable or not. So here I would like to just shortly mention that within the ferrules, not only graphite Vespel, but also with graphite, we can have different profiles of the ferrules available. So we can either can have straight ferrules, reducing ferrules, 2-hole ferrules, 3-hole ferrules, or blanking ferrules, so the ferrules without any holes. So depending on your application and your needs, different profile will be needed, but the most common one are either straight ferrules or reducing ferrules. And I've mentioned here that we do have also available metal ferrules. And the siltate metal ferrules, they have been specifically designed to overcome the problems, issues associated with use of the graphite ferrules. So I hope you remember from our last session about the columns that sometimes the pieces of the graphite can get stuck in the column and can interfere with our analysis, with our results. So the metal ferrules are ideal to overcome this issue, and they are recommended for the MS interfaces due to their strong seal on capillary columns, so it will reduce the air background. And we do have those ferrules also available in a seal-tight, finger-tight version. So the finger-tight, as the name's calling, they can be fitted by hand without any tools. So this will minimize the possibility of over-tightening the ferrule. So there is no possibility of doing that, so we will not break any columns. Also, the metal ferrules, they practically don't have a temperature limit, so are very versatile, can be used even in the high temperature applications. And here there is diagram of how the metal ferrules are installed. On the left side, we do have expanded diagram of the injection port interface. On the right side, we do have expanded view of the MS interface. And here, the last bit about metal ferrules, the finger-tight ferrules, they are pre-swaged onto the column before fitting into either injection port or on our detector interface. So Pre-swaging will make the ferrule staying in the same position all the time. So we will have our columns installed correctly all the time in the injection port and in our detector interface. So I hope you remember as well that the distances between the ferrule and injection port is very, very important, where our tip of the column is sitting in our injection port as well as in our detector. And here we've got the comparison of the chromatograms of the signal, which we will be getting using the metal ferrules. We will eliminate the air signal, where with graphite Vespel ferrous sometimes we can observe the signal for an error in our mass spec. So within the siltite range, so siltite technology, we do have also available unions for connecting either any pre-column, so the guard column, or two columns together, where we do multi-dimensional GC. So the siltite microunion is using the double-ended ferrule. So the two pieces of the tubing are meeting together in the middle. So we don't have any dead volume, and it is going through the deactivation process, the same as our liners. So the siltite microunion will not interact with our analytes. So it is providing us a high inertness. The next connection within our GC, which we can use, is the splitting of the signal, so splitter. And within our range of the products, we do have SilFlow. And SilFlow is stainless steel microchannel device. And it is enabling us the splitting signal and multi-dimensional complex applications. So I will show you on the next slide what can be done with the SilFlow, how it can be used. So going from the left, we can have one injector and sample going through the splitter onto two different columns into two separate detectors, or our sample can be injected, go through the one column, and then can be splitted into two detectors. And three-port splitter, another variation. We can inject our sample. The sample can go through the pre-column, and then the signal can be splitted, and part of the sample can go into split band or analytical column, and this will provide us a solution for overloading the column in case we are not able to inject lower volume of the sample. The four-port splitter can be used for backflash, and another variation of the splitter SilFlow is the Dane switch, which is enabling us to analysis of multi-dimensional GC, so the first dimension column and the second dimension column. So I hope that you know now what ferrules are available, how important it is sealing of our system in the GC. But to choose the correct ferrules for our instruments, we need to know three things. So, what is our instrument brand and model, or what fitting type and size this our instrument has? What is our column diameter? So different diameters of the column will require different hole size of the ferrule. And what material of the ferrule we would need. So mainly what temperature rating we need, or as well as if we do have, what detector do we have to choose the right material as graphite Vespel, or metal. So here is the table with the general guidance on what ferrule ID, so internal diameter, is required for different internal diameters of the columns. So 0.4 millimeter ID columns will be suitable for columns with 0.25 or less millimeter ID. 0.5 hole size ferrule will be suitable for 0.32 millimeter ID columns, and the larger ones, 0.8 millimeter hole size, is suitable for 0.53, so wide bore capillary columns. So talking about the connections and how important they are, so we don't have any leaks. Here are examples of what problems we can encounter when our connections are not great, so are poor. So the normal chromatogram on the left top is looking nice. Peak shapes are good, nice for analysis. Then we can observe various problems arising from our connections. So the peak size can be reduced. We can observe tailing, fronting, or splitting of the peaks when our connections are not made great. And this can be observed straight after installation of the connections. We can see the same problems arising from the columns, as I've explained in the last session. But this time, the problematic peaks, so tailing, fronting, will be visible straight away if the issue is associated with the poor connections. But with the columns, if the issue will be coming from the columns, so from the degradation of the column, the change will be gradual. So we will not see this straight away, but over the period of time. So going back again to the topic of the GC consumables and why do we need to change them regularly, and why we need to check them on a regular basis. I hope after this session and the last sessions, you're well aware what consequences we can see and how our consumables can help us to improve our results. So here are the key things to have in mind to know how often we should change the GC consumables. We should keep logbook for each GC, so keep the track of how many injections have been made. When something is going wrong, we should document what was done to fix it. Also, using all the information from our logbook, we are able to develop a preventative maintenance schedule, which will help us to improve our work and reduce the downtime of our GC. So I would like to remind you that within Trajan portfolio, we do have all the consumables needed for your GC workflow, for your GC needs. And today we covered the gas filters, splitters, unions. But during the last 4 sessions, we've been talking about syringes, GC septa, injection port liners, as well as the columns. So I hope you got a little bit more knowledge now after our presentations, which will help you to choose the correct consumables. But if you still need any help, please ask either your older colleagues, more experienced chromatographers, or please reach out to us. We are always more than happy to help. And I would like to thank you all for being present during those 5 weeks. And thank you for your time, everyone. And I would like to thank you also our host, organizer, Nova Analytica, for organizing this and enabling us to